So it's 16 past, so I think we can slowly start the lecture. So today, so last time Marcin was showing you low tree depth colorings, and essentially this is one of the main decompositional tools in class of bound expansion, and also in overlapping classes, by the way. And he showed an FPT algorithm for the subgraph isomorphism problem on class of bound expansion, which essentially boiled down to computing a low tree depth coloring and then trying to find the subgraph in question in each of like k tuples of colors. Yes, this is more or less what happened. And this could be rephrased as saying that existential first order model checking can be done in linear time in class of bound expansion, as Marcin was trying to sketch at the end of the lecture. And it was also announced that actually this existential is not really necessary there. Namely, simply model checking first order logic on class of bound expansion can be done in linear time. And this is a pretty difficult result. In the beginning, we thought we will not cover it during this course, but it turns out that we are going a little bit faster than we expected with the material. And therefore, we decided that this is an important thing, so we will show you the proof, because we essentially have all the tools. As I said, this is a pretty technical result, maybe not technical, but complicated in terms of the number of steps that you need. So it will take us some time to present it. I estimate that we should be done within this lecture, but it may happen that I will extend the lecture by 10 minutes. I hope it will not happen, but in this case I will have a slightly shorter tutorial and the break will be sort of shifted. But it makes sense to do it in one go. Yes? So just to say that in the beginning. Good. So first order model checking on sparse graphs. Probably not all of you are that well versed or that familiar with first order logic and general notation there. Marcin introduced basic stuff, but let me remind you what is first order logic and how we can think about it on graphs. So let's start with an example. Let's write an example formula. For instance, a formula phi that takes two vertices. Variables in our logic will always be attached to vertices of a graph. And this formula will say that distance between x and y is, say, at most 3. So there is a path of length at most 3 between x and y. So how can we phrase it? We can say that there is a first vertex on this path of length 3 between x and y, and second vertex on this path of length 3 between x and y, such that the following holds. First, there is an edge between x and z1, or x is actually equal to z1, and there is an edge between z1 and z2, or z1 is actually equal to z2, and there is an edge between z2 and y, yes, or z2 is actually equal to y, yes? So this formula expresses that there is a path of length at most 3 between x and y, right? Because, well, if there is a path, I can just quantify those z1 and z2 to be the vertices on the path, and if there is a path of shorter length, then I can put z1, for example, equal to z2, yes? So this is a formula which expresses the distance between x and y is at most 3. So for instance, I could phrase that the distance is exactly 3 by writing that the distance is at most 3 and the distance is not at most 2. Yes? So in this small examples, you already see essentially all the features that you can use. You can use quantification over vertices. You can use Boolean connectives. You can use negation. Yes, in order to construct your formulas. Yes, you could also use universal quantifier apart from the existential quantifier. But note that universal quantifier is actually only the syntactic sugar, because you can write it as existential quantifier with double negation. Yes? So this formula is called existential. We formally say that it belongs to the existential fragment of first order logic, because the only thing it does like a block of existential quantifiers, yes, followed by a quantifier-free formula. Yes? This formula, on the other hand, is not existential. Even though if I just replace it with this formula, I would only use existential quantifiers, because this existential quantification is under negation. Yes? So existential formula looks like that. Exists, 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 and then a quantifier-free fragment. Yep. So this formula is not of this form, and indeed you can always replace the universal quantification with existential quantification, so you can always get rid of those at the cost of introducing some negations. Yes? So I think that this was something that Marcin did not really explain well the last time, so I wanted to clarify. So this is a first order formula that checks some property of two vertices, x and y. Yes? So these two things are called free variables of a formula, and these are variables that are not bound by any quantifier. Yes? So then a formula just expresses some property between the three variables, some relation between them. Yes? So a sentence, first order sentence, is a formula without free variables. Yeah, so a sentence just says something universal about the graph. For example, there is no triangle. Yes? There do not exist free vertices such that they are mutually adjacent. Yes. Okay, so essentially a formula looks more or less like this. This is a formula phi that is applied to some couple of variables. So in here we talked about logic on graphs. So graphs are a special case of something called relational structures, or just structures. And the structure is always consists of a sigma, which is a signature of the structure, also called vocabulary. Yeah? So this vocabulary or signature just expresses the language of symbols that we are allowed to use. So in here, the signature consisted only of one relation symbol, which was binary, yes, which was the edge relation, being adjacent. Yes? But in general, we can have, for example, like binary relations, like adjacency. Yes? We can have unary relations. For example, I don't know, maybe there is a set of red vertices in the graph. Yes, and there can be a unary relation, which will be sometimes also called a unary predicate, that just checks whether a vertex is red. Yes? So this formula R of some vertex U will be true if and only if the vertex is red in my structure. Yes? There can be also like ternary relations. So some relation with of arity free and so on and so on. And I will also allow so-called nullary relations. These are just relations without any like of arity 0, and they can be all, like, you can see them only as like flags that are added to the structure. They are true or false in the structure, but they are not bound to any vertex. Yes? Okay, so structures, they consist of signature. They are always over some signature, and then a structure A consists of universe. In our case, this will be the vertex set of the graph, and for every relation R in the signature, yes, I have some realization of this relation, call it RA, which is just a subset of the universe to the power arity of the relation. Yes? So in a sense, like, if I have a binary relation, then the realization of this relation in the structure, yes, is just a set of pairs. Yes? So in like one binary relation is the best suited for expressing directed graphs, and if you want to express in this language undirected graphs, you just assume that this binary relation is symmetric. Yeah? There's an edge between u and v, if and only if there's an edge between v and u. Yes? So during this talk, we will, during this lecture, we will be mostly using some binary relations, yes, multiple ones, yes, and multiple unary relations. So most of our structures will have like a lot of different colors on vertices, which will be encoded using unary predicates. Yeah, so this is just a generalization of graphs in a sense. Yes. So if I have some structure A over some signature, yes, I can think, I can have also some FO formula, say, over this signature, this vocabulary, sigma, this is the vocabulary of my structure. Yes? And now if I'm given some tuple, which is an evaluation of these variables, yes? Then I can apply, like, I can check whether phi on this evaluation of the variables is true. Yes? So I will write it like that for evaluations of variables. And this can be, think of functions from the variables in the set of variables x to the universe u. Yes? So this is just the set of evaluations of variables in the tuple x. This is the tuple of variables. Right? So if I have such an evaluation, which is just saying that the first variable is this vertex and the second variable is that vertex, then I can check in the natural way, is, say, phi of A true in my structure A. Yes? This is a valid question. Yes, and it can be true or not. And the notion of being true is defined naturally by the natural semantics of this quantifiers and these Boolean connectives. Yeah? And if it is true, then we write it like that the structure models that phi of A is true. So this is phi of A is true in A. So you read that A is the model for phi of A. Yep. So now, it is also quite convenient to think about all these structures and so on via the lenses of database theory. So think of this whole structure A, this graph that we are given as a database, yes, with different vertices and different relations between those vertices. Yes? Then what is an FO formula? It is nothing else than just a query. Yes? This FO formula that we have here is just a query given a graph. Give me all the pairs of vertices at distance at most free from each other. Yes? So to FO formulas, I will always sometimes call FO queries, simply. Yes? So now given such a formula phi, yes, and the structure A, we can think of the set phi of A, which is just the set of all tuples. So this is a formula with 3 variables x. This is the set of all tuples of all evaluations of variables such that phi of A is true in A. Yes? So in a sense, if I now apply to a graph this formula, distance at most free, this phi of A will be the set of all pairs of vertices that are at distance at most free from each other. Yes? This is just a language to speak about it. Yes? And you can think about this as query evaluation in a database. Oh yes, I think that we are sort of settled with the language that we are going to use, and now we can again recall what results we will prove. Oh, one more thing about classes of structures. So during this course, we usually think about classes of graphs. Yes. Now we make it a little bit more generalized. So if C is a class of structures, like a class of structures is just a set of structures, but we implicitly always assume that if we were talking about some class, all these structures are all over the same vocabulary, the same signature. Yes? So when we say about a class of graphs, this is a class of structures over the vocabulary of graphs. Yes? So we now say that C has, for instance, bounded expansion if the class of Geisman graphs of structures in C has bounded expansion. Yeah, so what is a Geisman graph? This is just a graph on the same vertex set as the universe of our structure, where we put an edge between two vertices whenever they appear in the same tuple in some relation. So in a sense, whenever you have a relation, say, of arity 4 between 4 vertices like that, in the Geisman graph you just put a clique of size 4 between them to indicate that they are bound by some tuple in some relation together. Yeah? So in a sense, if we are talking about graphs or structures with arity at most 2, yes, the Geisman graph is just the graph, essentially. Yes? So this is just how we say that that a class of structures is sparse if it is sparse if and only if the class of its Geisman graph is sparse. Yes? And similarly, nowhere dense, bounded tree depth, I don't know, bounded tree width, and so on and so on. Yes, you can just lift all the definitions from classes of graph to classes of structures in this way. Good. So now the theorem that we are going to prove today, hopefully, is that if C is a class of structures over some fixed signature, yes, so this is implicit in here, with bounded expansion, say phi is a FO sentence, is an FO sentence, then it can be decided given some structure A from my class, yes, whether my sentence is true in linear time. Yes, so I'm given, say, a graph that is sparse. I'm given some FO sentence which expresses some property of this graph, and I can check in linear time whether this sentence is true. Yes? And the linear time with respect to the size of the structure, and the size of the structure is well-defined natural, let's say, by the size of the Geisman graph. Yes? The total number of edges and vertices. And if it is bounded expansion, well, the number of edges is linear, and therefore this is essentially equivalent to saying just the size of the universe. Yep. Okay, so this is the theorem which we are going to prove. There is another theorem that is tailored to lower dense classes. So let me write it here. So if C is nowhere dense class of structures, and F is again FO sentence, then I will call it already by the name it should bear, FO model checking on C can be done in time order of, this is a fixed FO sentence. In time, as you would expect, the size of the structure to 1 plus epsilon. Yes, where this O notation hides a factor that is dependent on the sentence. Yes? So in here, this is the running time order of the size of the structure, so linear. Here, as one could expect, this is not really linear, this is almost linear. Yes? In time this for any epsilon larger than 0. Yes? So this is a theorem proved first by Dvorak, Kral, and Thomas in 2011. This is a theorem of Grohe, Kreutzer, and Sibet. I think 2014. Yeah, so these are pretty young results. We will now give a proof of this because we have all the tools necessary for the proof of this. This proof that we will show is not the original proof. It is our reinterpretation and remodeling, quite far-reaching actually, remodeling of the original proof. But the proof of this theorem is completely different, in a sense. Meaning we are unable to lift the ideas from this proof to that proof. So actually we would be super happy if we could apply the same strategy to prove a theorem on lower dense graphs, yes, as we can do on bounded expression graphs, and the reason for this will be apparent in a moment when I will sketch a strategy that we will use for this. Good. Is it clear so far? So the strategy that we will employ will be that we will show a procedure which is called quantifier elimination. So essentially the idea is that you already know, more or less, how to make this model checking if our sentence is existential. Yeah, there exists one vertex, there exists a second vertex, there is a third vertex, and so on, such that there is some relation between them. Yes? Because then for existential sentences, the witness for this sentence being true is of bounded size, yes, and therefore you can catch it using low tree-left colorings. Essentially, this is the idea. Yeah? But now if you have quantifier alternation, there exists a vertex such that for every other vertex, something happens. Yes? This becomes more complicated. The witness, like checking the witness already requires more effort than just looking at the induced substructure. So what we will try to do, we will try to eliminate quantifiers from our sentence while enriching the structure with more information, so that at the end we will be checking only a very simple formula, which can be done using low tree-left colorings. Yes? So to make it more formal, quantifier elimination will work as follows. We are given some sentence phi, or actually a formula. It will be more convenient to think about formulas. Yes? So some FO query. And we are given some structure on which we would like to evaluate this query. Yes? And we will transform this formula to a new formula, phi hat, which will be quantifier free. Yes? And we will transform this structure into a new structure, A hat, which will be over the same universe but which will contain much more information than A. Yes? This transformation will be done in linear time. And the property that we will want to maintain is that this query on this structure is equivalent to this query on this structure. So the property that we need is that phi of A is equal to phi hat of A hat. Yes? If I evaluate query phi on my structure A, I get exactly the same tuples, exactly the same result as evaluating the new query that is simpler over the more complicated structure, enriched. Yes? So one thing that, one additional property that we need is that, okay, these two structures are over the same universe, but I will also want that the edge set of the Geifman graph of I hat is a subset of the edge set of the original Geifman graph. So in a sense, I can only lose edges in the Geifman graph. I do not introduce new pairs of vertices that are bound by some relation. Yes? So the graph, in particular, the Geifman graph of this structure will be still sparse, because it will be a subgraph of a sparse graph. Yes? So let me, given this idea, let me now state a lemma, or maybe you can even call it a theorem, that we will prove. So let's see, be a class of structures of bounded expansion. Let phi be a formula with some free variables. So there is a new class of structures, a class C hat, which also has bounded expansion. Yes, a new formula phi hat. Yes, in the new signature. Yes, with the same free variables, and what? And a linear time transformation that takes an instance that takes a structure from C and outputs an enriched structure from C hat, such that these things hold. Right? So essentially we will take any structure from our class with a formula, yes, and we will transform it, this structure will enrich with information while we simplify the formula to being quantifier free. Yes, while preserving exactly the answers. Yes. Now, we will not exactly get this statement, at least not as I presented it here, because I will now need to add an asterisk to this quantifier free. Namely, we will not work just with relational structures, so structures with relations, but we will add, we allow unary functions in signatures. Yeah, so a unary function is just a function. Yeah, if you have a variable f, you can apply a function to it and get a new element f of x. Yes, so a unary function, if this is my universe, you can view it as a essentially set of pointers. Maybe this guy by f points to this guy points to himself, this guy here points like that. Yes, this is a example unary function. So now, of course, you can add these unary functions to the Geifman graph. So in the Geifman graph, we also consider such edges binding the argument with the value. Yes, so this is natural. But most importantly, when you think about quantifier free formulas, we allow using those unary functions there. Yes. So for instance, if I write, say, f of x equal to g of y, yes, this is for me now, if I allow those unary functions, this is a quantifier free formula. Yes? Observe that actually I can get rid of those unary functions by replacing them with relations. So if I have a unary function f, I can always replace it with a binary relation, say Rf, yes, which will be always true if and only if y is f of x. Yes? And then if in my formula I use f of x at any time, I can replace it with, say, writing there exists x prime, yes, such that Rf of x and x prime, and then using x prime instead of f of x. But this introduces a quantifier, an existential quantifier. So by this quantifier free, I mean quantifier free allowing using functions in my quantifier free formulas. I could also say, for example, f of x is red. This is also allowed. Yes? And we can always get rid of those functions at the cost of adding more existential quantifiers. Yes? So this is a technical feature about this quantifier free. Yes?
So will this function have the property that they are always between two elements that are adjacent in Geifman graph?
Yes.
So basically this, for us, this means that it will be always a neighbor.
Yes. It will be always a neighbor. So essentially every vertex will have a constant number of pointers to its neighbors. You can think it this way. Because like this, the number of those functions is bounded by the size of the signature, which is always a constant. Yeah. Good. Any more doubts and questions and stuff at this point? So what is important to understand now is that we will prove this theorem by giving this quantifier elimination procedure. Yes? What is different between this proof and that proof for lower dense graphs is that the proof that we know for this doesn't give a quantifier elimination. And we would really want to have quantifier elimination because, as we will see in the tutorials, this gives us a lot of generalizations of just model checking. So say enumeration, counting, and so on. And this becomes much more difficult in this sense because we do not have quantifier elimination. Okay, but this was a digression. Okay, so before we proceed to the proof of that theorem about quantifier elimination, let us see how this theorem implies the theorem of Dvořáky and Thomas. Yes? So, okay, this I can erase. So if I now want to prove this theorem, what I do, I take A, yes, I take formula phi, which is a sentence, yeah? It doesn't have any free variables. And now I apply the quantifier elimination to this structure A and formula phi, yes, getting a new structure A hat in linear time, and a new formula, a sentence actually, because it has the same free variables as phi, yes, such that phi of A is the same as phi hat of A hat. So what is phi of A when phi is a sentence, doesn't have any free variables? Yes? This is just true or false. Yes? And this is just true or false. So this equality, when phi is a sentence, just means A is a model for phi is true in A, if and only if phi hat is true in A hat. Yeah, so this preserves the and we know that this is quantifier free. Yes? So what is a quantifier free sentence? It's a weird animal, yeah? Because I cannot say anything about any variable because, well, there are no variables and I cannot introduce variables using any quantification. But observe that in our language we allowed for nullary relations, for relations that do not take any variable. So this sentence is then just a Boolean combination of nullary relations. Right? So a Boolean combination of nullary relations, I can check in constant time whether it is true or not. Yes? Then check whether A hat models phi hat in constant time. Yes? So this theorem is more general than the theorem about just model checking sentences. Yes? It gives more information about general formulas. Okay, so we are now ready to start proving the theorem about quantifier elimination. So the idea of the proof will be to proceed in 3 steps. Proving the quantifier elimination statement for more and more complicated classes of structures. We will start with very basic classes of structures, namely forests of bounded depth. Yes? I will define what is a forest of bounded depth in a moment, but I guess that most of you can imagine what is a forest of bounded depth. Yes? If I have forest of bounded depth, I will be able to lift this result for classes of bounded tree depth. And this should not be that surprising, because, well, a structure of bounded tree depth can be sort of encoded in its decomposition, which is a forest of bounded depth. And this will be exactly the intuition behind this lift. And finally, so this is encoding in the decomposition. And finally, from class of bounded tree depth, we will lift to classes of bounded expansion, and this will be done using low tree depth colorings. Essentially similar as we did the last time, because it will turn out that we only need to think about existential statements, existential formulas. So the nice feature of this proof schema, which is different than the original proof, is that actually the main combinatorial meet, the main combinatorial trick, why this whole result is possible, happens already in here. So we will be working with a very simple setting, and then in this very simple setting we will see already the main idea. Okay, so what are then forests of bounded depth? So say that C is a class of forests of bounded depth if the signature of my class consists of, I allow some nullary relations, I allow some unary relations. So there can be some colors, some unary predicates on the elements of my universe. Yeah, so the nodes can be red, green, blue. Actually, we have a lot of those colors, as you might expect. And I allow one unary function parent. Yes? And moreover, parent induces a forest of bounded depth. Yeah, so how it looks, I've got in my universe some nodes, some elements, and I've got this parent relation that looks like that. To define the parent relation on the roots, I can, for example, say that they point to themselves. Yes? And I've got some unary predicates, some unary relations. So, for example, I can think that there are some orange vertices, and say that these vertices are orange. Yep. Okay. So this is a class of forest of bounded depth to state it formally, and the statement that we will prove is the following of quantifier elimination lemma. So if C is a class of forests of bounded depth, phi is a FO formula, then from this C and phi, I can get a new class C. This is also a class of forests of bounded depth, and a new formula phi hat. Yes, this is the, which will be quantifier free. Yes, and moreover, if I'm given some forest T, I can transform it into an enriched forest T hat. Yes? This forest belongs to C, this forest belongs to C hat. Yeah? Such that phi of T is equal to phi hat of T hat. So essentially only I preserve the output of my FO formula, and T hat is, I would call it a recoloring of T. So T hat differs from T by just saying I have the same universe, I have the same parent relation, I only change the colors of vertices. I actually will only add some bazillion more colors, yes, in order to rephrase formula phi into a quantifier free formula phi hat, so that this new information in T hat can be used by phi hat to reason in a quantifier free way whether phi is true or not. Is it clear? Yeah. Good. Okay, so this is the lemma that we will prove. And as usual in working with first order logic, we will do induction on the structure of the formula. Yes? So a first order formula, well, it has some quantifiers, it has some Boolean connectives and so on, but essentially you start with very simple formulas, atomic formulas like saying x equal to y, or there is a relation between x and y and so on. Yes? And you build up larger and larger subformulas using Boolean connectives, using existential quantification, and so on. Yes? So we will proceed bottom up over the structure of this formula phi, proving the statement for larger and larger subformulas. Yes? So proof. Yes. Proof. So the proof will be induction on structure, on subformulas of phi. Okay, so let's do it step by step. So first the base case. So atomic formulas. So atomic formulas are formulas x equal to y, or let's say parent of x is equal to parent of y, and so on. So is there any problem with atomic formulas? No. Why not?
They are quantifier free.
Yes. So they are already okay. Already quantifier free. Yes? Because at the end we wanted to have a quantifier free formula, which is equivalent to our formula. Yes? And if the formula is already quantifier free, there's nothing to do. Yes? I have t hat equal to t, c hat equal to c, and phi hat equal to phi. Yes? Already done. Okay, so then I've got, for instance, negation. So I have, for instance, subformula, say psi of some y. Yes? And now I would like to get the statement for formula not psi of y. Yes? And we already have the statement proved for psi. So what do we do?
Transform psi and add the negation.
Negate psi hat.
Sorry?
Negate.
And negate psi hat. So if I have my 3t and psi, yes, by the induction hypothesis, I can transform it into psi hat, t hat psi hat, which have exactly the same output on t hat as psi had on t. Yes? And now, so we know that psi of t is equal to psi hat of t hat. Yes? And now, if I have this equality, I also have equality that not psi on t, yes, gives the same tuples as not psi hat on t hat. It will just give the complement of those tuples. Yes? So we do this transformation, and now we have that not psi hat. Yes, so the formula equivalent to not psi is just not psi hat. Yep. So this is very easy. You just apply the induction assumption and you negate the result. Okay, so far so good. So the next thing that we need to consider is alternative. I've got some formula psi of, say, y, or psi prime. Or do you know of any other Greek letters?
Phi.
Phi. I did not want to use phi because we use it here. Let's say phi. Okay, I've got an alternative of two subformulas. So what do I do?
Apply induction twice.
I apply induction twice. From t and psi, I can get some t hat and psi hat. From t and psi, I get some t, let's say, double hat. And, or maybe this will be t hat 1. And this will be t hat 2. And this will be psi hat. Yes? So now what you do, you take t hat, the enriched 3t, yes, as the, I will write it like this, as a superposition of t hat 1 and t hat 2. So this superposition means I take these two trees, they are exactly the same tree as the original one, just recolored, and I just add all those colorings together. Yes? I add all the unary predicates from this tree and all the unary predicates from that tree. Yes? So I've got double as many unary predicates, but that's fine. Yes? And now if I want to have a query that is equivalent to psi or xi, then I just take the query equivalent to xi, and I take its alternative disjunction with the query that is equivalent to xi. Yes? And then the tuples output by this query, yes, are exactly the tuples output by that query or by that query. So again, this is applying induction hypothesis and essentially symbol pushing. Yes? So now we come to the interesting part. Namely, we need to deal with quantification. So we have a formula that exists, say, as z, such that, say, psi of y and z. Maybe this is a subformula, I will call it psi of y. Yes? This is a general step with quantification. Note that we do not need to deal with conjunction, because conjunction can be modeled by disjunction and negation. And we don't need to deal with universal quantification, because universal quantification can be modeled by existential quantification and negation. Yes? So this is the only step that is missing. Given that we can do the job for the formula psi, we want to do the job for the formula xi, which is just exists z such that this holds. Yeah? So now this is the main case that we need to do. So first observation is that without loss of generality, psi is quantifier free. Why so?
From induction.
By induction. Because if I now apply my induction assumption to psi, yes, what I get an equivalent quantifier-free formula over some enriched forest, over some recolored forest. So now if I applied it, I got this equivalent instance. If I have a reasoning that applies to quantifier-free psi, I can just combine the two things. Yeah, I can combine the induction assumption and then a reasoning for a quantifier-free psi. Yes, because I will just apply this reasoning to an already recolored forest. Yeah, so this is like just a composition of two things, of two arguments. Okay, so this is a quantifier-free formula. So now comes the main observation, the main combinatorial part of the proof. Namely, what can a quantifier-free formula essentially do in a graph, in a rooted forest? It cannot do much. So let's say that here I've got my rooted forest. Say a rooted tree to make it simpler. And here I've got, say, let's say A is the evaluation of the variables in Y. Yes, so this is a tuple A. Yes, A1, A2, A3, A4. Yes? If my formula psi, and maybe here I've got some evaluation of my variable B, of my variable Z, sorry. And this is called B. The only thing that my formula psi of YZ, yes, can access, yes, during the evaluation, are the ancestors. Yes, of A and B. Because this formula is quantifier free, so it can only speak about those vertices and their parents and their parents' parents and so on and so on. And because the whole forest is of bounded depth, this is a bounded number of vertices. Yes? This is actually, this formula can speak only about this tree induced by the ancestors of vertices A and B. Yes? And can only speak about the mutual, like, what is the color of this vertex? Is this vertex red? Yes? Is the parent of this guy equal to the parent of that guy? And so on and so on. This is the only thing that a quantifier-free formula can speak about. So let's make it more formal. So let's say that if I have some tuple A of vertices and some tree T, then by T of A we denote the subtree induced by ancestors of A. Yeah, so this is this orange tree that is there. Yes? So now I claim the following, as we will see in a moment, or maybe I will write like that. So let's say that S is a tree it's a tree over a forest, over the signature. Well, the signature of our initial class C, with leaves labeled by variables of Y and Z. And I will say that base formula or basic formula let's call it alpha of yz, yes, alpha s of yz, is a formula, the subtree induced by the ancestors is isomorphic to S. Yes? So in the most restrictive case, what a quantifier-free formula can say is it will just take all these things, it will get all the ancestors, and it will precisely say what color which ancestor is of, and which ancestors are equal. Yes? So a base formula is a formula that perfectly specifies everything that is induced by the ancestors of my variables. Yes? By saying that this subtree of bounded size, yes, is isomorphic to some fixed tree S, where this tree S is essentially this template, this pattern. Yeah, so this tree S looks like that. Yes, and there is the special variable Z that is quantified here. This is, say, y1 up to yk, and this is formula Z. And now what I claim is that my formula, every quantifier-free formula psi is equivalent to a disjunction of basic formulas. Oof. So this is a scary-looking sentence, or scary-looking claim, but actually there is not much inside in it, because what we say is that if I have my quantifier-free formula, it can only speak about the ancestors of the guys. Yes? So if I look at the ancestors of the guys, the subtree of them can look like that, or can look like that, or can look like that, and so on. There are finitely many, constantly many isomorphism types of this subtree induced by the ancestors. So for some isomorphism types, the formula will be true. For some of them will be false. Yes? So I can rewrite my formula as saying this isomorphism type happens, or that isomorphism type happens, or that isomorphism type happens, and so on and so on. Yeah? So I can rewrite it as a large disjunction over saying this is how the ancestors look like. Yes? Note that this formula perhaps becomes much, much larger, because the number of those basic formulas is a constant, but it's like exponential in the size of the signature. Good. So now, what this means is that this formula psi I can write as, say, a disjunction over some family of trees of this base formula alpha s. Yes? So now, if I now think about my formula that I'm really interested in, the formula with z quantified existentially in front, this is the same as that. Now comes a trick. Existential quantification commutes with this junction. In the following sense, this is the same formula as saying this junction over this set of base formulas, there exists a z such that alpha s of y z. Yes? I can, instead of saying there exists a z such that something or something or something, I can say something or something or something, and in each of them quantify this z existentially. Good. But observe now that if we are able to deal with such formulas, then we already know how to deal with this junction. We did it here. Yeah? So it suffices to prove the statement for all those formulas with this being a basic sentence, a basic formula, because then we will combine all the results using the reasoning for this junction. So the outcome of all this argumentation is the following. Without loss of generality, we can assume, recall that we are speaking about formula psi of y, which is exists z such that psi of y z. Yeah? Without loss of generality, we can assume that psi is a basic sentence. It's a basic formula. Yeah? So observe that this whole proof is essentially, the scheme of this proof is that we are simplifying and simplifying and simplifying to a very concrete case where the whole thing that the formula is speaking about is the following. So we are given some tuple of variables y. So these are some vertices in my graph. Say A is an evaluation of variables y. We already see their ancestors, and having access to y, we can check exactly what are their colors. And the only thing that we are interested in this formula is whether I can also find some z that sort of looks like that. It is like a leg that is attached to this orange tree. Yeah? So now if I want having access to those vertices, those evaluations of y, when I want to know whether such a z exists, essentially the intuition is that in my enriched tree, we will, in this vertex, memorize whether such a z is here, whether I can extend this leg there. So that the existence of such a z I will be able to check by taking any vertex here, going up, and checking here whether I memorize that this z is here. That's the main idea of the proof. Yeah, so now we are going to really enrich the tree with more information. Good. So how do we do it? So let's say that this vertex, that here I've got the z, yes, and here this vertex, this is my tree S, so this pattern of my basic formula, yes, and let's say that this path here I will call a path P. So a path P is up to the child of this least common ancestor of z and any other vertex of y. Yes? So now I will say that in a tree T, a node, maybe I will say that this vertex is at level k, this vertex is at level, say, L prime, or maybe L plus 1, while this vertex is at level L. Yeah? Note that this tree S perfectly specifies at which level the vertex should be, if I have an embedding of this S in a tree T. So in a tree T, a node at level, let's call it U, at level L plus 1 is good if I will draw it first. So here I've got some vertex U, and it is good if I can draw this blue path. Yes? If I can find a descendant here, V, at depth K, such that this path has exactly the same color pattern as this path here. Yes, as this path in my tree S. So this I mean by good. Yeah? So this being good means I can't find an example there. Yes, I can find an example of evaluation of that there. Okay, if maybe I will not specify it in written, but this should suffice. Yeah, so a vertex is good if it is at level L+1 and it has a descendant at level K, such that the path between them has exactly the same colors as the path in my pattern S that I was looking at. Yeah? So now I define this enriched tree. And now will be one more trick. So I have my tree T, and now I would like to add to T more information to create a tree T hat. I will add only some unary predicates to my tree in order to keep track of those good vertices. So what I will add is that I will add to my tree in here. First, I will add a unary predicate selecting, so a unary relation selecting good vertices. Yep. So this unary relation selects vertices at level L+1, exactly those vertices that are good. Yes? Below which there is a witness. And moreover, for vertices at level L, so those vertices 1 up here, memorize how many good children they have. They have up to threshold the size of y. Okay, so what does it mean? So a vertex at level L, here, maybe I'll make a zoom. A vertex at level L has multiple children. Yes? Some of them are good, some of them are not. Yes? I would like to memorize for the vertex how many good children it has. So I have one unary predicate for vertices at level L that have no good children. I have one unary predicate for those that have one good child. For those that have two good children. For those that have the size of y, good children. And for all of them that have more than the size of y, I have one unary predicate saying infinity. Yes? So all in all, these are, if I'm not mistaken, the size of y plus 2 new predicates. Plus 3. So tree T is now tree T hat is nothing else than tree T enriched with this information. And now I claim that from my formula phi, from my formula xi of y equal to that, this I can transform into an equivalent formula xi hat, which will be quantifier free. So what the formula xi hat does? Well, it takes a tree. Yeah, so now I define the formula xi hat. It takes a tree and it gets some evaluation of y, some evaluation of the variables. Yeah, it works on some tuple. Yes, it doesn't see this z. Yeah, it needs to check whether such a z exists. So what it does? First of all, like what does this formula say? This formula is the same as this alpha s. So this formula essentially speaks about the subtree induced by the ancestors has precisely this shape. So first of all, this formula checks if ancestors of y are as should. Yeah? So the subtree induced by the ancestors needs to be as it should be. Yes? And now we need to additionally check whether I can find some evaluation of this z, whether I can find a leg like that. So observe that this vertex I can access. Yes? Let's call it T, because this is a parent blah of some, say, x1 or y1. So in this vertex, I can check how many good children it has. Yeah? By this unary predicates here. And now if I want to find this leg here, extending here, I check whether it has at least one good child. But this is not really sufficient, because if it has one good child, this one good child can look like that. And the tree will be different, because this thing could go here. But observe that for this child here, the child inside my my ancestors of y, yes, I can check whether this guy is good or not, because I can access it from here. Yes? Similarly, all the other children that are inside the ancestors of y, I can access. So what I check is, I check if the number of good children of T is larger than the number of good children of T that are ancestors of Y. Because if this number is larger, then I can add this additional leg to this good child. And this check I can do using those predicates, because this number is at most the number of the size of y. So it doesn't matter whether the number of good children is y plus 1 or y plus 2 or y plus 3, it's always okay. Yes? Yeah, so this is the formula of psi hat that is now quantifier free. It speaks only about the ancestors of y and the information that is collected in them. And this essentially finishes the proof for the case of rooted forests, which was the most difficult part of the proof. And now we will lift it up to classical bound expansion through low tree-depth colorings. Yes?
What if this pattern S is not a tree, but it's a forest?
Perfect question. I was just going to ask if anybody sees a problem in this proof. So can you repeat what is the potential problem in this proof?
So here we assume that this blue leg just attaches to the to one of the patterns, and then it's easy. But it can happen that it's not.
Yeah.
It just like goes to its own root, which is in different components.
Indeed. So this is a corner case that I wanted to sweep under the carpet and then ask about your carefulness, your care after the proof is finished. So what could happen, essentially, that this pattern S is not necessarily just a tree, it can be a forest. Yes? It can look like that maybe here are those variables that we are given, those variables y. Yes? And what the stupid variable z that is quantified does, it looks like that. It is in a separate part. So does anybody see what do we do in this case?
We also have another predicate for roots. Of
Yes. So we define in a similar way good roots, roots that can extend to a witness for the existence of z. Yes? So this takes care of that unary predicate selecting good roots. So what do we do here? Where do we store this information about the number of good roots? In nullary relation. So in a sense, there is no root of roots in which we would store this information about the number of good children, yes, to store. So instead of storing it in a vertex, we store it in nullary relations. And this is the only place in the proof where we actually use the nullary relations, which actually were used in the proof of the model checking result. Yeah? So the proof will actually do it. Yes? It will add those nullary relations at some point and then use them to reason about at the end of the proof of model checking sentences. Good. Very good question. Thank you for being for taking care of that. Good. So now we have proven the result for forests of bounded depth. Now we want to prove the results for structures of bounded tree depth. So the lemma now for bounded tree depth, the quantifier elimination lemma will be as follows. So say C is a class of bounded tree depth. Now phi is a FO formula. Say phi of x is an FO formula. So now what we say is that there exists, then there is a class, I will call it C hat, of bounded depth forests. And phi hat quantifier free formula in the vocabulary of this, such that every structure A from C I can transform into a forest, say T hat, from my class of forests, yes, in linear time, yes, such that if I apply my original query on my original structure, this is the same as applying my new query on my new structure. And I need to take care also of this Geifman graph preservance. So the second thing is that the edge set of the Geifman graph of the forest should be a subset of the edge set of the Geifman graph of the original structure. Yes? So observe that the Geifman graph of a rooted forest is just this forest. Yes, as a graph. One thing also that now I recall, we did not check one thing in the previous proof. Can you see what we did not check? So when we were speaking about this adding new predicates, this is a transformation that takes T and outputs a rooted forest T hat, which is enriched with new information. I need this to be computable in linear time. Yes? Because we want the whole algorithm to run in linear time. But it is an easy exercise to show that finding good vertices is an easy bottom-up dynamic programming on this tree, which can be done in linear time. Okay, good. Okay, so we got back to here. Yes? So now this is a statement for classes of bounded tree depth. I essentially want to transform class of bounded tree depth into a class of bounded depth forest. Yes? Preserving the same answer to the queries. Okay, so the proof. First of all, I claim that I do not need to have this quantifier free here. Yes? Suffices to have phi at not necessarily quantifier free. Why?
Because we can apply what we have just shown.
Because we can apply then the quantifier free elimination from bounded depth forests. Yes? If we prove this without the quantifier free, we can then combine this, compose this with quantifier elimination for the bounded depth forest that we get at the end. Yeah? So this is just the question of taking a structure of bounded tree depth and encoding it in a bounded depth forest. So this will be actually sort of easy. So I've got my structure A. This is a structure of bounded structure from my class C, which is a class of structure of bounded tree. Yes. So then what I do first is I compute any DFS forest, call it T, of the Geifman graph of A. I take the Geifman graph, I compute it, I run DFS on it, I computed a forest. So what can we say about the forest T? What is its depth?
2 to 3 depth.
Yes, so if the depth, the tree depth of C is at most D, then the depth of T is at most 2 to the D. Yes? This was one of the exercises we had about the tree depth, because the tree depth of a path of length 2 to the D, more than 2 to the D is more than D, yes? Then if this DFS forest had depth more than 2 to the D, this would contradict the fact that the tree depth of my original structure is at most D. Yes? So by just running a DFS algorithm, we've got a forest of bounded depth. It's slightly larger, but still. So observe now that by doing this DFS here, I've got the following property. The edge set of T is a subgraph of the Geifman graph of the original graph. Yes, all the edges in my forest T are actually edges in the original graph. Yes, this is essential for having this property. So now construct T by taking T and adding unary predicates. So essentially I now take this decomposition tree, this T, yeah, it looks like that. Yeah. This is just a tree, a forest actually. And I encode my whole original structure, yes, in this using unary predicates, yes, so that essentially in first order logic I can recover the original relation. So for instance, let's say that my original structure A was a graph, yes, so I've got one binary relation, H. Yes, so suppose, for simplicity, suppose A is a graph. Yeah, so I've got only one edge relation that I would like to encode in here. Yeah? So how the edges can look like on this picture? So this is the tree T, the forest T, and now, as usual in the tree depth decompositions, yes, the edges of my graph connect ancestors with descendants. Yes. So now we would like to add to this tree T some unary relations so that I can recover edges of my original graph, yes, using those unary relations. So let's look at one edge. Yeah? How will I encode it? I will store this edge in the lower vertex by saying that in this vertex I store that this vertex, say V, is adjacent to its parent I, parent to the power I. So if there is an edge like that, I add a unary predicate saying that there is an edge between V and the parent of its parent and of its parent and so on, I types. There can be multiple edges, yes, So I will have one relation for the parent, one relation for the grandparent, one relation for the grandparent of the grandparent, and so on and so on. Yeah? So I add how many around D new unary relations. Yes, selecting vertices adjacent to their I-fold parents.
Do we add the relations or to the power of d as we just used?
Ah, 2 to the d, of course. Sorry, a constant.
Yeah.
Yes, because well, the depth of this is 2 to the d. Yeah. So now, if now I have this formula phi, the original one, and which works over the original structure, and I need to rephrase it, like to rewrite it to a formula working on this, yes, that has the same meaning. So now suppose that in this formula, I checked whether there is an edge between x and y. How do we write it using those new predicates? We write it, for instance, that x is an ancestor of y, and y has the information. Or y is an ancestor of x, and x has the information about the existence of this edge. Yes? Because this edge can look like xy or yx in my decomposition. So I check whether one of the vertex has the information about the existence of the other. Yeah? So whenever I see in this formula an edge check like that, adjacency check like that, I replace it with a formula saying this. Yes? Using the new unary predicates. Yeah? Which is equivalent now in this encoding. And essentially that's it. So we did it for binary relations. And now if I have ternary relations, essentially if I have a ternary relation, the three vertices in a tuple of a ternary relation, because in the Geifman graph they create a clique, they need to be on a single path like that. And I will store the information about this triple being in a relation in the lowest vertex, because it can access the other ones. Yes, so this proves this lemma without the quantifier 3, yes, for the class of bounded tree depth, and then we can combine this with the quantifier elimination for forest of bounded depth to get this with a quantifier 3 formula here. Okay, so as I said, as I expected, sort of, I need 15 more minutes to finish this proof. So I will now finish this proof and we will get shorter tutorials by 15 minutes. So 15 more minutes and we should lift this result to cluster bounded expansion. Okay, so what can we erase? I think this part can erase. So observe that in this proof actually nothing that interesting happened. It is just a rewriting of a formula to a formula with a different encoding of the structure. The main combinatorial trick is in the case of bounded depth forests. And now we are talking about what? We are talking about cluster bounded expansion. So we have one cluster bounded expansion C. We have a formula phi. Yes. And say we have a structure A from my class C, and we would like to transform this to a new enriched class of structures C hat to a formula phi hat that is quantifier free. Note that we can use here the functions, and this every substructure from C we should be able to transform in linear time to a structure A hat from C hat such that phi of A is the same as phi hat of A. Yeah, so this is just a recollection of what we are trying to do. So the proof, and the guide paragraphs. I'll just write it for the record, but I hope that you already remember. Yeah. So the proof, again, we do induction on structure of phi. Yes. So we go bottom up from atomic formulas. Yes. And by induction, we construct more and more complicated structures A, in which we can rephrase the original subformulas using quantifier-free formulas. So again, base case, easy.
What are you trying to prove actually? Because I got lost.
We are trying to prove, so this is the theorem about quantifier elimination that we started with.
Okay.
That from a class of bounded, given a class of bounded expansion and a formula phi, yes, we can transform it into an enriched class of bounded expansion C hat and a quantifier-free formula phi hat, such that every structure from here in linear time we can transform to a structure in here, where this quantifier-free formula selects exactly the same result as this formula selects here.
Does we want bounded 3 depth on the right?
No, this will bound expansion.
Okay. So, but here this C hat will simply differ. Only the signature will differ, right?
Yes, the signature will differ.
And this will be the only difference.
Yeah, meaning the graph will be the same. The graph will be the same, the signature will be much, much larger.
Okay.
Yes, so we will do induction on the structure of phi. In the sense we take all the subformulas of phi and we prove this statement, this transformation, for the subformulas bottom up. Okay, so for the atomic formulas, is it easy?
It's the
Yeah,
same.
quantifier free.
Yeah, because they are quantifier free. So the negation. Is it easy?
It's the same as it was.
Same argument. Apply induction hypothesis and negate the result. Yes? Disjunction. Again the same?
Yes.
Yes. Okay, so now we come to the interesting case. So now we have formula of the form, again, psi of y being equal to there exists a z such that psi of y and z. Yes? So again, without loss of generality, this is quantifier free. Because I can apply induction. Yes? And I got a new class of bound expansion enriched, and then I apply the reasoning for this class of bound expansion and already enriched structure that transformed this into a quantifier free query. Right, so now what we do, so this structure over which this works, yes, it is again a class of bounded expansion, yes, but it can have some functions, right? I don't want those functions. So eliminate functions from psi. In the sense like psi, this quantifier free formula, it can use some functions. It can say that f of x is equal to g of y. Yes? I don't want this. Yes? So what I do, I take this structure over which this works, and instead of every function f, I introduce a new binary predicate, binding every argument with its value, yes, and I existentially quantify the variable the f of x. Yeah? So in this way, I transformed this formula that exists as z, psi of yz, into a possibly more complicated formula, but existential one. Yes? Because all these results of the functions are quantified existentially. There exists a result of the function such that there is a relation there. Yeah? So at the cost of now having z being a tuple of variables rather than one variable, yes, we can assume that in my structure over which this works, there are no functions. Okay, but now this is an existential formula. And we can apply the understanding that we have about existential formulas and closed-treated colorings. That's the main trick. Yeah? So let, I don't know, lambda be a, so let's say k is the total number of variables. Yeah? And let lambda be a 3-depth k coloring of the Geisman graph of my structure. Yeah, so every k tuple of colors, every k colors induce a subgraph of 3-depth at most k. And now comes the main claim. So let's say that some nice Greek letter, lambda. Lambda is the set of all subsets of k colors. Yeah, so then the size of lambda is a constant. Yeah, it is the number of colors, choose k, and the number of colors is a constant. Yeah. So for every, so now comes the main claim. This, or maybe I will call it the right way, psi of some tuple A holds in A if and only if there exists a subset of colors such that this psi of A holds in, let's write it A of x. So in the substructure induced by the colors from X. Why so? Because, well, this query, psi, it looks like that. So what this query actually does in my structure, there is some tuple A which is an evaluation of the variables y, and it just asks, is there some additional evaluation of the variable z such that something happens only in this area. And this area is of size at most k. So it is completely covered by some k tuple of colors, subset of k colors. So if this holds in A, this means that for this tuple of colors corresponding to A and the witnesses, yes, this will hold in this induced substructure. And if it holds in this induced substructure, then, well, the same witnesses are okay in the whole graph. Yeah? So actually observe that this set is of bounded size. So this exists. It's not really an exist. It is a disjunction. Yeah? So now you see more or less how the proof will work. This query will be equivalent to this disjunction of queries over structures of bounded 3-depth. And for structures of bounded 3-depth, we already know what to do. Yeah? So let's make it formal. So to make it formal, I just observe that structures A of x for x in my lambda, in my subset of colors, belong to a class I will call D. These are all structures over the vocabulary of C of 3 depth at most k. Yes, these are induced substructures. Yes, and they have 3 depth at most k because this was a 3 depth k coloring. Yeah, so every set of k colors induces a substructure of 3 depth at most k. This is a class of bounded 3 depth. Yes, so we apply bounded 3 depth case. Yeah, and by applying bounded 3 depth case, I can take my formula psi of y and I can transform it into a formula psi hat of y, which is now quantifier free. Yes, such that if I apply this psi on the substructure induced by x, this is the same as applying this quantifier free rewritten formula on the substructure after enriching it according to the bounded 3 depth case. Yes? This is actually a bounded depth forest. Because the bounded 3 depth case was outputting bounded depth forests. Yeah? So now what do you do? Now the final structure A hat is the superposition of all structures A of x hat. I take all these bounded depth forests, yes? I assume that they are over disjoint signatures, just to make sure that relations do not merge. Yes? So in particular, each of those bounded depth forests has its own parent functions, and all these parent functions are really different. Yes? I take all these structures and I just put them on top of each other. I just flatten the whole thing. Yes? So now my structure A hat consists of as many as the size of lambda bounded depth forests put on top of each other. So it has that many parent functions together with like size of lambda times a bazillion unary predicates on top of it. Yes? Plus some nullary predicates. Essentially, this is what A is about. And now, the final query phi hat, psi hat, is nothing else as what we had there. At this junction, a constant size disjunction over all sets of colors of saying, well, this psi hat but working on colors from X, yes, of Y. Let me now think about it. Maybe, okay, let's roll back a bit. So if I want to check, so what do I need to do to check whether psi holds in A of X? I need to check whether A, meaning whether these variables Y, they are in X, because otherwise it's certainly not true, meaning this thing doesn't capture already the arguments, not to mention the witnesses. Yes? And then I need to apply my formula in my A of X. So what I do, I write here that Y colors of y belong to x. This is one thing. And for this, I add to my structure also colors of my coloring lambda using unary predicates. Yes? And I write that this quantifier-free formula holds on tuples y. Yes? But note that this quantifier-free formula, this we obtained from the quantifier elimination for the bounded 3-depth case. And this formula uses the signature of this. Now, this signature, we actually made them disjoint. So we need to also adjust this formula a bit so that it uses exactly, say, the parent function, for example, corresponding to x. Yeah, so I will write it like that to indicate that we take this formula that we got from the quantifier-free elimination for the bounded 3-depth case, and we adjust the vocabulary used by it, yes, to the parent function for ax and the predicates of ax, and so on, because these are different predicates. And from this claim, it follows that we have what we wanted. Yeah, because this claim says that this formula exactly expresses, yes, the existence of witnesses within the various color sets. And now to check that this holds, it's already lost. To check that the Geifman graph of the new structure is a subgraph of the Geifman graph of the previous structure, we use the fact that in this bounded 3-depth quantifier elimination, yes, we were only taking edges that were edges of the original graph. Yeah, so we do not introduce any new edges when smashing all these structures together. And this concludes the proof.
Why is this linear time? Especially why finding this set D is linear time?
Why this is linear time?
No, I mean above, belong to D. How can we find the set D? Or
well, D is just a class of structures, yes? This.
Yes.
So how this works algorithmically? We compute a low 3-depth coloring of the Geifman graph. This we argue that we can do in linear time by doing, say, fraternal augmentations, doing greedy coloring, and so on. This was the last lecture. Yeah? Now, when we have this bounded 3-depth coloring, yes, for every tuple of k colors, and there are constantly many, we apply the quantifier elimination for the bounded 3-depth case. The bounded 3-depth case quantifier elimination boils down to encoding the bounded 3-depth graph in its 3-depth decomposition obtained from a DFS. DFS is linear time. Yes? This encoding you can easily see that you can do in linear time. This rehashing re-encoding the bounded 3-depth structure into a bounded depth forest. Then you apply the quantifier elimination for the bounded depth forest, and then we argue that this enrichment procedure that we had also can be done by dynamic programming bottom-up in linear time. So all of these things can be done in linear time. Good. Are there any more questions? Okay, I think we deserve a break. So we meet in half an hour, so 35 here, so that we all have a break. There are some problems here to think about during the break.